Okay, let's unpack this. So today we're doing a deep dive into something that, we all think we know, but maybe we don't. The scientific method.
Right.
And our mission here isn't just to go over the steps you memorized in school. We're aiming higher. We want to explore how this whole systematic process actually creates foundational truths.
What we call axioms.
Exactly, axioms. And this is the really critical part, how this same ancient rigor is being adapted right now to tackle one of the biggest challenges we have, leading and validating advanced AI.
Yeah, and the sources we're pulling from are pretty fascinating. We've got stuff on formal logic, some really detailed diagrams of the scientific cycle, and texts that connect all these dots, from investigation to establishing truth in modern problem solving.
So if you're out there trying to get up to speed on something complex, and you need to do it with absolute rigor, this framework we're discussing is, it's portable. You can apply it anywhere.
From the lab to, like you said, managing tech systems.
Absolutely. So let's start with the core engine, but not like a boring checklist. Let's talk about the philosophy behind it.
Good idea.
The whole thing is a systematic process, obviously, for investigating observations. But its real genius, I think, is that it's not designed to prove anything. It's designed to destroy premature certainty.
That is the key distinction, isn't it? It all starts in the same place. An observation, a question. You see something you can't explain.
And you can't even move forward until you've clearly defined that problem.
You have to research it first.
Which pushes us right into step 2. Formulating a hypothesis. Now, people call this a guess, but it's not really just a guess, is it?
Not at all. The sources are really clear on this. It has to be based on broad spectrum, unbiased inference. You're pulling from everything you can find.
And here's where the rigor really kicks in. The whole method forces you to prepare for falsification right from the very start.
Yes. You're not trying to prove yourself right. You're actively setting up the conditions to prove yourself wrong.
Which just elevates it so far beyond a simple hunch or speculation. I just found it so powerful. The system itself is built on a foundation of systematic doubt. So once you have that hypothesis, you move into the core loop.
The experimentation and comparison part.
You design your test, you run it, and then comes the most important part, the measurement.
The comparison phase. And this is where you pit your observed results, so what actually happened,
right,
against the expected results. That's what should have happened if your hypothesis was correct.
And if they don't line up, if you get a discrepancy.
That's the feedback loop. The process demands you go straight back and refine the hypothesis. You don't get to just ignore the bad result.
This is what stops confirmation bias in its tracks. And our source material really highlights that this refinement, it's never a closed loop. It's always open to being proven wrong later.
It's an inherently humble process. You have to go back, do a deeper dive, and refine that starting premise before you can even think about moving forward. It's basically systematized intellectual humility.
That is the perfect phrase for it. And it's so relatable, right? Even outside a lab, you're trying to fix some messy problem at work. You start with an assumption. Hypothesis A. You try a fix.
And it fails.
It fails. Your observed results do not equal your expected results. So you don't just throw up your hands. You circle back, you take that new data from the failure, and you create a smarter assumption. Hypothesis B.
It's the ultimate learning engine.
And that engine just keeps turning until you get consistency. And when the experiment finally does support the hypothesis, then we can talk about drawing a conclusion.
But even then, success isn't the end. It's really just the beginning of the validation process.
Exactly. The next step is all about continued investigation, reporting. If your first hypothesis holds up, great. Now you have to run more experiments, often different kinds of experiments, based on it.
And, critically, you need confirming results from independent experiments. Someone else has to be able to get your result before it gains any real status.
And that's the bridge, right? That's how we get from a simple conclusion to something foundational.
It's a huge leap. The confirmed finding is proposed as a theory. People start acting on it. And eventually, if it holds up time and time again, those findings get published as a premise. Or, as we've been saying, an axiom of truth.
Okay, so let's nail down that word axiom, because it's fundamental, but it gets used a little differently depending on the field.
It can be slippery.
So an axiom, or a postulate, is just a statement that's taken to be true. It's the starting point for any other reasoning you're going to do in that area.
And the etymology is just wonderful. It's from the ancient Greek, axiosma. It means that which is thought worthy or fit.
Something that just seems self-evident.
Or at least commends itself as a good starting place.
But that's where the definition splits a little, right? Between classic philosophy and modern logic.
In classic philosophy, an axiom was seen as a statement that was so self-evident, so universally true that you couldn't even argue with it. Undeniable truths.
But modern logic and math have a more functional view.
A much more functional view. An axiom is simply the accepted starting point for reasoning within a defined system. It doesn't have to feel universally true to everyone on the planet. It just has to be the ground rule for the game you're playing.
That distinction is so crucial, especially when you look at how we build systems of knowledge. I mean, think about something like geometry.
Perfect example.
You have a theory about shapes in space. The non-logical axioms, the postulates, are your starting rules. Like the parallel postulate in Euclidean geometry. It just defines the kind of space you're talking about. It's a rule of that specific game.
And then separate from that, you have the logical axioms. And those are the rules of reasoning itself. They're the scaffolding for how you think.
Like the idea that if you say A and B are true,
then A has to be true on its own. It seems obvious, but it's a rule that has to be defined. The logical axioms tell you how to reason, while the non-logical axioms tell you what you're reasoning about.
So the big idea here, the intellectual payoff, is this concept of axiomatizing a system of knowledge, which means showing that all the complex claims, all the big theories, whether it's physics or math or even, business strategy, that all of it can be derived from a tiny, well-understood set of sentences, from those core axioms. It's about building a skyscraper from just a few absolutely solid cornerstones.
And once you have those cornerstones, you can trust the structure. You know that any new claim, as long as it's derived logically from those axioms, is standing on solid ground.
Okay, so we've built this foundation, a systematic process, iterative, built on proving things wrong, that leads to these foundational premises. So what happens when we take this centuries-old method and apply it to something bleeding edge? What does all this mean for how we handle complex modern tech, like leading AI?
What's fascinating here is that the approach doesn't just apply to, the outside world. It also applies to how we structure and manage our own tools.
How so?
Well, our source material makes the case that the best way to use AI right now is to apply that same investigative rigor internally. To learn how to be a team leader, essentially. To break down a problem and assign different AI agents to be the expert team members.
That's a really powerful reframing. So you're not just using the AI, you're applying the scientific method to the process of building a solution with the AI.
Exactly. The whole iterative loop of observation, hypothesis, refinement, that becomes your project management cycle for the AI team.
Okay, walk me through that. So an AI problem pops up. How does it mirror the lab process?
It mirrors it perfectly. Step 1. Define the problem. You have an unexplained observation. Maybe an AI model is giving weird results. You define the effects. You research those effects. You figure out what you know, and just as importantly, what you don't.
And then you move to the hypothesis.
Step 2. Hypothesis purpose. You make your initial guess at the root cause. But with AI, there's an extra layer. You also have to list all the other things, the symptoms, that might be disguising the root cause.
Because it's so complex.
Exactly. So you build that hypothesis based on unbiased inference, and you prepare to falsify it, same as in the lab.
Which brings us to step 3, the testing.
The methods testing. And this is where the AI leadership part really comes in. You brainstorm a whole sequence of tests using your different AI agents or models to get to the truth. And the standard for truth in these digital systems, well, the bar is set incredibly high.
This feels like a huge takeaway for anyone in tech or data analysis. Our sources define truth in this context, not as just, a simple consensus.
No.
It's the correlation of Six Sigma results from different sources.
And you really have to understand what Six Sigma means to feel the weight of that. It's a statistical measure of near perfection.
We're talking what, like 3.4 defects per million?
3.4 errors per million opportunities. It's an insane level of confidence.
So why? Why is that level of rigor? 99.99966% accuracy. Why is that the standard for establishing a truth when you're dealing with AI?
Because the potential for hidden errors is it's exponential. You're dealing with data drift, with systemic bias, with non-obvious flaws in the model. A simple 95% confidence just isn't good enough when you have, say, human safety or critical infrastructure on the line.
So you need multiple independent tests. Different sources or different AI agents all have to agree at that Six Sigma level before you can call it a reliable premise.
That's it. So that comparison, phase observed results versus expected results, it's happening constantly across multiple expert agents, and they all have to hit that near perfect mark.
Which makes that iterative refinement loop even more intense.
Oh, absolutely. You test the hypothesis with your agents, you analyze the correlated results. If they don't hit Six Sigma, you go right back to the hypothesis, redefine the problem, re-engineer the methods. It's the same skeptical loop, just applied inside a massively complex digital world.
And the cycle ends in the same way. Once you finally get that near-perfect correlation through repeatable independent tests,
then the finding is robust enough. You can propose it as a theory. You act on it, you integrate the solution, and you publish those results as a new foundational axiom for that specific AI system.
the integrity of the process holds. It's still observation-driven, hypothesis-led.
Falsification-based, and built on the need for independent, high-confidence validation. It's the structured path from doubt to dependable truth, whether you're in a chemistry lab or managing a huge AI operation.
So we started this deep dive by mapping that systematic process observation, hypothesis, experiment, conclusion, and we've connected it directly to how we create our foundational beliefs.
The scientific method at its heart is really a structured argument. It's built on falsification and comparison, and that's what gives you the confidence to turn ideas into reliable knowledge.
And we saw that the real power of this is the ability to axiomatize a system, to show that all the complex claims in a field can be derived from just a small, well-understood set of sentences, the core axioms.
It's about finding those cornerstones.
So we want to leave you with this. We encourage you to take this systematic approach and think about your own field of endeavor. If you had to axiomatize the knowledge in your professional or even your personal life, what would those cornerstones be? What are the 3 or 4 core non-negotiable axioms, those starting premises taken to be true in your system, that all your other claims and decisions are built on? Think on that until the next deep dive.